Welcome and good evening, everyone. Really glad to have you here. All right, so we'll start with the introduction, then we'll have expert talk, followed by the Q&A. For your Q&A, kindly ask the questions in the Q&A location and not the chat. And we'll have a final conclusion and closing remarks. So just to remind you that we have some house rules that needs to be followed. Hope everyone is at a safe location and are seated comfortably and you are aware of your surroundings. The session will start in another 1 minute and the questions will be managed in the Q&A in the MS Teams. So do not enter any questions in the chat message. And importantly, we'll share the feedback form. Kindly share your valuable feedback, and whoever shares the feedback will also receive the certificate of participation. All right. So welcome once again, and it's really glad to have you all here. So today we'll be seeing Mini speak, and we welcome Mini here. She is working with Dell Technologies, Bangalore, in the domain of embedded system security, with more than 28 years of experience in the domains such as defense, semiconductors, consumer electronics, substation automation, and industrial measurements. She has published multiple research papers, filed patents, and often speaks at various forums. Outside the mainstream work interests, he has fascination of numbers and colors, which has manifested into various fractal images. That's her hobby. She, of course, has won multiple awards and done multiple professional certifications. She has completed her master's in embedded system from BITS Pilani and also bachelor's in computer science from the University of Kerala. Currently, she is pursuing her PhD in embedded system security, and she's a huge motivation to all our OT professional community and to all the women out there. Glad to have you here, Mini. And of course, we'll be sharing our details. Kindly follow, join the WhatsApp, also follow the previous Tech Talks and subscribe to our YouTube. Mini, thank you again and glad to have you here. You can start sharing your screen.
Okay, thank you. Thank you, John. That was a nice introduction. Good. And since you mentioned about the fractal images, if you look at my LinkedIn profile, you will be able to see some of them for a sample. Like whichever once in a while random, there are some images there. That's not to do with OT security, but then it is more like more of a hobby number that I'm behind for quite a long number of years. I hope my screen is visible.
Yes, it is visible.
Yes,
Go ahead.
okay. So today we would take around 40 minutes, 45 minutes for going through the session. And if you have any questions, feel free to ask then and there. There is no need to keep your curiosity towards the end. Or if it is something which is breaking the flow of the conversation, you can hold it till the end also. That's fine if it's out of what we are talking about. So today we will be talking about building a fortress, securing IoT devices with root of trust. That's what the topic that we have picked up for the day. So primarily we will be speaking about what are the challenges with IoT device security and how can the concept of a root of trust save us from so many of the security issues that we will be talking about, or typically in the IoT domain, the security challenges that come, what we do with that with a root of trust and how does that help us. That is the focus for today. Then we will also have some kind of an introduction on the architecture, how these security concepts are applicable to IoT devices. That's also something which we will try to cover. Okay. Okay, so when we talk about Internet of Things, uh, let us look at how these Internet of Things shape up, how it is architectured, and where do they communicate. So this could be thought of as say an industrial IoT. That could be one environment that we are talking about, or it could be a smart city kind of an example, or it could be some kind of a power system. There could be many of those kind of environments that we could look at it as an example. This is a generic architecture where we will talk about where these industrial IoTs or even any other general purpose IoT devices come into picture and the architecture. So what we are talking in the left side, those are the things which we are talking. There could be a house, or there can be ship mounted, or within a plant, all that. The left side of the columns that we are talking, those are the things. It could be from the sensors, actuators, your IEDs, RTUs, PLCs, all that could be the things that we are talking about. And typically there would be some local communication that happens. And the local communication can be wired or wireless. Both of them can be, because these days we also see a lot of these wireless instruments also coming into picture. Like there are things which are SIM based, those narrowband IoT, all those kind of devices, or they could also be wired communication. So you will have some kind of a local communication network, and at some moment they will get into the internet boundary that we are talking there. Uh, from there to the right, it's more of public domain. We do not have any kind of a physical control on what happens beyond the internet boundary, because that is accessible to a whole world of people. Of course, the authentication, authorization, all those are there, but then it's not like it is hidden physically from the world when we are talking on the right side of the red line, the internet boundary. Whereas on the left side, okay, we can say that, okay, we have some kind of a physical control there. Like within a plant or something. Then we have the edge gateway. Typically, we do not want every single device or the Internet of Things to be talking to the internet without an uncontrolled manner. So in a typical architecture, we will have an edge gateway. It could be a small edge gateway, typical, or it could even be something that maybe your mobile application collects some and then it is talking. That also could be a manner, or it could be an edge complex itself. So that depends on the scale at which we are talking. And then on the right side, the edge gateway could typically be putting your information onto a cloud platform. That could be your Azure IoT Hub, or your AWS, any of those kind of platforms that would be. And then there would be applications. It could be mobile applications, or it could be web applications, or there could also be just REST API based information that is available from the cloud. And then you may be showing it for your other analysis and further inference making. That's what you are seeing that as an application. These are the main components that we are talking. And considering this to be the architecture, we will be focusing on what would be the security implications of the devices on the left side. We are not going to cover the security of the internet or the security of the application or the edge gateway in this presentation. The focus is considering that the risk factors involved and all are all this, how do we secure the IoT devices themselves? So let's see, have an overview of what kind of security threats happen in the IoT devices. Like what all can come in. This is not an exhaustive list, but I have put some kind of a representative examples that would help us to understand what can go bad. Okay. So the first item, what we are seeing is, it could be the software itself is vulnerable, because we see that a lot of CV is getting announced in the world. Every now and then it keeps coming. And even it could be coming from the, say, okay, I don't make vulnerable software. That statement doesn't hold anymore. Like every companies who are designing, and then even the development teams, there are of course vulnerabilities. So we accept that there are vulnerabilities. It could be kind of a buffer overflow, or could be authentication failure. Like you could also look at the OWASP IoT top 10. That is some kind of examples that you can look at to understand what kind of vulnerabilities are there. Or even the OWASP top 10 from a web application point, that also is some kind of example. So the software itself is vulnerable. And even if we say, okay, we designed, we took care, even after all the care, there are third-party libraries. Like example, OpenSSL, there are a lot of security vulnerabilities which are coming up in the OpenSSL, even though it is a well-stabilized software stack, still they keep coming. And these are all used very common, very often in all these IoT devices. So the software is vulnerable. So how much ever we are talking that we have taken care, there are known vulnerabilities which are existing. So patching the system is important. even understanding that the individual IoT device, does it contain that vulnerability or not? That's also important. How do we make out? Those are all the kind of security threats that are existing. And then there are privacy threat. Like even if you are not talking of the vulnerable software, you could be tracking the location and the usage. There could be traffic interception that is happening, because as we saw, the IoT devices, they are talking to something else. They are connected, whether it is in the local network or in the public network. And in certain examples, like uh, say a smart city example, it's not that always they go through a controlled manner in an edge gateway. Right? The SIM based examples which I was telling, narrowband IoT and all, there could be places where the devices themselves could be talking. And then the third column, see the cloning. Cloning could be another one dangerous manner. So you say that a well respected, well reputed development firm, they develop it well, they have all the security controls, go through all the things, and then you release a product. But it could be that the devices which are out there, they are counterfeit devices. It could be somebody would have cloned those, look and feel, everything is the same. And then maybe you have just missed, and then someone else is taking that, taken over, and then doing another device which has the, like Cisco networks, which a while ago there were some kind of examples that has happened. Every look and feel is the same, but then they are no more. You don't have that trust on the same as what it comes from the original. And then the devices that are cloned, they get into the network, and then they could be the ones who are there to perform attacks, various kind of attacks. And these may not have the same kind of security functionality, or even the functional robustness that we are expecting from a well tested and well developed product. Or they may have a degraded functionality and could even be going to the level that uh, these kind of adversaries have taken, cloned the device, and they would have included some backdoors into it, so that they can still have more advanced attack capability. Those are another set of security threats that can happen with IoT devices. Let's look at some more. Then this malicious substitution. Replace a genuine device with a low quality one. So that means it's a damage to the reputation. At the same time, the functionality is broken. You don't get the same robustness as you are expecting. Eavesdropping, you have some kind of communication channel that are happening. Somebody could be eavesdropping on the keying material, so then they can get over the complete data, and then your privacy is lost. And it could still be that somebody is eavesdropping on the security parameters and the configuration settings. Then also we lost the privacy not only for the data for that session, it could also be that they can use that further over a long period of time. Not just that session is compromised, but then once you get keying material and the security parameters configuration setting, or they could change the configuration to something which is less robust, all that are also possible. And then we have this typical person in the middle, and the person in the middle can happen at any phase. Like in the OT security, when we are talking, there are, you get a device, then they go through multiple phases. There would be system integrators who take, and then the owner operators, before it reaches to the owner operator, there could be other people to intercept and then work. Commissioning, that could be another time when it can be vulnerable and they may be under attack. The system integrators time, commissioning phase, the testing time, or the operational phase, all those time, these are vulnerable. If you look at these kind of supply chain kind of issues that we were talking about, like malicious substitution, for example. And then some more, say it could be that the physical device itself may not be something which is replaced or put a substitution, but somebody could have put, if there are flaws in the firmware update, somebody could have put a malicious firmware into the device. It could be a poorly maintained firmware. That can be one case, or the firmware again get into with additional security flows like the backdoor which we are talking about. And if somebody gets hold of the hardware, that is the next one which I am talking. So if they get hold of the hardware, and if they take out the memory, and if they pick out and look at all the pins, and then look and then collect the private key information from that physical device. So if they are not kept in a stored in a secure storage within the device, like a trusted platform module, that's what I'm talking about as a secure storage. If you don't do all that, you still have the, like somebody get hold of a physical device, and are they able to extract sensitive information, which typically could be keying material, which they can use in a class attack, which is on a other scale of devices. Like what information you get from one single device, are you able to use it for a class attack? Say, for example, if someone get hold of a firmware signing key, of course, that is usually within the premises of the development environment, not within the device, then you can create anything else that is possible. In a similar manner, if there are keys which are used in the device, it should never be possible that one single instance key leak should not happen, that somebody can mount a class-based attack. That should not be possible. And there are also limited memory and compute in the typical IoT devices. There could be a denial of service attack that could happen. This is another class of attack that can come in. So we just looked at what is all that the device are vulnerable. It's not just that the firmware is vulnerable, even if you have a robust firmware inside, which is also not the case in a realistic manner. There are so many other issues that can happen, and this is not the exhaustive list. As I put some examples so that you have a appreciation for what we are talking, the kind of issues that we are talking. Now let us look at the life cycle of a typical IoT device. Like I put as an example from a manufacturing to your decommissioning. That is what I'm talking about. Like you can relate it to whatever device that you are familiar. Like if since most of the crowd here is interested in OT security, you could look at your IEDs, RTOs, PLCs, or measurement instruments, any of those kind of things which you can look at. Okay. So typically what happens is you manufacture in a factory and then put your firmware inside. You may put some kind of cryptographic key material inside. And then from the factory, everything is done. The factory can be operated by the own people themselves, the vendor themselves, or it could also be, in a lot of cases, there can be outsourced factories. The factory may be operated by someone else. So those factory where you are manufacturing, that in itself should be secure. You should protect your factory environment so that you don't get any of those keys leaked. Like say, for example, I'm telling identity keys. How do you give identities for individual devices? So that can be, there will be HSMs in the factory. Are you operating those hardware security module which you use for generating your CSR and getting it signed and shipping it out? So is that done in a secure manner? Who has access to that? And is there any insider threat that is possible? All those are to be considered in the manufacturing phase. And then further it get into supply chain. When you say supply chain, as I told before, it can be in multiple hopes can happen there. One could be from the owner integrators, it could be, or the pre-test that is happening before you deploy the system. Then it could be during the operation phase. All those are something before it gets into your actual primary functionality. That is all what we are talking about, the supply chain. There are a lot of conversations that are going on in the industry about the software supply chain that is coming up from NIST and everywhere. But right now here, what I'm talking is not just the software supply chain, even the physical device, where all it go through, whose hand it goes through. Can someone put some kind of malicious information into it? Or is there a hardware tampering possible? All those are things which we are talking. And then provisioning. Provisioning is a step which we are talking about. How do you first time put the physical device into an operational stage? There are various examples which you can talk. I'm not going into this provisioning as a concept here, but if you are interested, then you can look up topics like say FIDO device onboarding, FDO as a provisioning protocol, or OPC-UA. OPC-UA recently, I think it's 2-3 years before, or less than 3 years, has published one specification for OPC-UA device provisioning. That's all about zero-touch provisioning. Like you take it, you connect it, it gets all the identity, network identity in the operational domain, and then it starts working. After that is the usual operation. Operation is the primary function that it is doing. It's doing all its work, whether it is measurement or whether it is controlling actuators or algorithm running, all that is what is happening in the operational phase. It's doing its primary function. And management is during the life of the device, while it is doing the operation, there are various other management functions that would happen. There could be something which goes bad and you want a part replacement, you replace and put a different device, then you should still work at the same level of security that it was working before. And other examples of management is firmware updates. Say you have understood that there are some vulnerabilities, you got it corrected, or it can be for functional basis, you do a firmware update. And after the firmware update, is it all coming down? And your regular maintenance, all that can be your part of your management of activities. And decommissioning. And decommissioning is important because you should never leave your device out into the open with secrets inside or customer data inside, because that's also a problem. So there should be sufficient erase mechanisms, a secure erase. It's all cleaned up and it is back to factory default. Sometimes it's even beyond what was put from the, you may be configuring information from the factory for specific customers, that also should be cleaned up. So nothing which is sensitive, no keying material should present in the device after your decommissioning. So that is the decommissioning phase. So through all this, you have the security challenges that comes at each and every phase. That is your identity and authentication. Is it coming from a genuine vendor? Or if a device that comes to you is from a vendor X, is that coming from the vendor X, or is it a cloned device coming from somebody else? And then in your supply chain provisioning, you need various access control that's possible, that's required for you to put them into an operational stage and do the work. And even during the operational stage, you need access control. Is that all in place? Those are your other security challenges. And the communication protocols. Do you have any possibility for eavesdropping? Are the protocols secure? Do you have some underlying encryption for confidentiality, such as TLS protocols? All those are what you are looking at in the other protocol challenges. Network security, are you talking to your talking partner, your other entity which you are talking? For example, your web browsers, if you have an embedded web server inside the device, for whatever be the purpose, then is the network security guaranteed? And the privacy, trust, fault tolerance is also one kind of security challenge, because can someone like us, what we told before, take down your system by overloading it with a lot of information? Resource exhaustion, is that are possible? Or when we are reaching there, how are you tolerant to that? And is that coming, fault tolerance need not necessarily be from an attack scenario, but it could be from your operational situation also. You may be reaching into cases where it is beyond your ability to handle. So is that all handled? So these are the kind of security challenges that comes up during the device lifecycle. I have one more diagram here, how it is running. It's kind of the similar concept that we are explaining. So when you look at the life cycle of the device, it is manufactured, installed, then you have commissioned, and the application running. After the application running, that is where it is the operational stage, where it is functionally, it is doing its purpose. And the installation, commissioning, those are all bootstrapping phases that would be happening. And then there could be maintenance phases that happen, like your application reconfiguration. You put a different configuration for the application, or it could be your software update that is happening. All those are things that are happening there. And then other milestones that happen in the devices, you are decommissioning or parts removal, when you are removing one and putting it back. And it could also be a re-ownership or recommissioning, like at the end of it, you decommission it, and then do you also refurbish and sell it again? There's nothing wrong with it. You can do that because you don't want to discard it from one operator to further. You can reuse it. If you are reusing, re-ownership and recommissioning, that's also one kind of a phase that the device is going through. So in all these situations, how are we able to manage the security in this lifecycle scenarios? And then in the supply chain, the kind of issues that happen, we can get into cloning, counterfeiting, tampering, and you may not have your application trustworthiness, your authenticity and integrity. That could also be a problem. And when whatever I spoke before, what happens when you look at a security point of view, from an identity point of view, we are shifting through different trust domains. Like the manufacturer, that is a manufacturer's trust domain. If you are, say, for example, the factory HSM, the device can trust the factory HSM because you trust things in that domain. In the supply chain, like your integrators and system integrators, the system integrators need to do various testing, configuration, all that. Then that is your trust domain. And during your operation, the network, say a plant, that plant could be your trust domain. You are, because you need to speak to other entities within the same trust domain. And during the service, it could be the same owner operator who is doing the service, or it could be that the service, say a case where the service is outsourced to another service organization. Then if they come with a laptop, then you should be able to configure and do your service activity. So that is another trust domain. So as you are moving through in the device lifecycle, it has to shift through various trust domains, and there should be also knowledge within the device to make sure that in this life stage of my life, I have to trust other devices in this trust domain. So there is a transfer of trust domain that happens during the supply chain and during your service and maintenance and your typically we use digital certificates for all this purpose. So when we are using these digital certificates, we should know that our identity is one, and the domain, which domain do I trust, that also should be known. And when we are during the operation, you don't trust the trust domain in the manufacturer, because it's already in the owner operator's place, it's already in the plant, the device vendor need not have to do anything. So as you change, you should also be able to change your trust domain. Say an integrator has finished the work of preparing everything and then given it to the owner operator. Integrators don't have anything to do with the device after that. So after that, they should not be able to do any work in the device. So that's the change of trust domain. So typically all these are done with the help of a device identity. That's what we are talking. And in device identity, let me give some basic introduction into what is the concept of device identity. If you are interested into learning more about some of the reference which you could use is IEEE 802.1 AR. They talk about IDAV-ID and LDAV-ID. These are the device identities. IDAV-ID is the initial device identity and LDAV-ID is the locally significant device identity. IDAV-ID, we say initial device identity, that is a birth certificate. So when the device is manufactured, it has to be known that, okay, this is from a genuine vendor. How do you establish that? In my previous steps, I was telling, how do you establish that this is from the vendor who claimed that it is from? That means the vendor can provide, the device vendor, the device manufacturer can provide a device identity, which is its initial device identity. There are various terms that people use for that. Some call it a birth certificate, some call an IDAV-ID, some call it as a initial device identity or long-term device identity. All those are told. So that is something which is done at the manufacturer time. It's to know that, okay, who manufactured the device, whom it is coming from, and where is the origin. So that can be established using your IDAV-ID. And the identity is a cryptographically bound identity to the physical device. So what typically happens is it's bound to the hardware. So there should be some kind of a hardware secure element like TPM, or it could be something within the integrated, within the SoC itself, there can be a secure element that is, say secure element means it should typically have the capability to generate public-private key pair. The key should remain within the secure element. The key should never come out of that. I mean, the private key should never come out of that. But you can do operations with that, like signing verification. And once the private public key pair is generated, you create an associated certificate from the factory HSM. So typically you generate a CSR and then give it to the factory HSM. They sign it and return it. So you have an associated certificate. So you have a key pair and an associated certificate. That's what we call as an IDAV-ID. So this identity is from the manufacturer. And what we call as a locally significant identity, because this identity is what identifies the device in that trust domain. So in the operational environment, the moment you are provisioning that device into an operational environment, it could be that we are providing an identity in that local domain, which we call as a locally significant identity. That means when you are provisioning it, as an example, which I told, the OPC UA device provisioning spec, that could be something which you can refer for an example of what is a provisioning. During the provisioning, you get a locally significant identity. Once again, it is a key pair with an associated certificate which is significant in the domain of operation. That is where we call as a locally significant. So based on that, you can establish trust. As we go through the phases which I was talking about, you can have an identity which is valid in that trust domain. And you use that to identify the device to that domain. So initial device identity you can use for the purpose of provisioning. After it is provisioned, you can use the locally significant identity. And then this is something all till now I was talking about devices which are kind of low in compute capability, typical IoT devices. But not all IoT devices are very small in compute. Though they are very typical, it's not. Like say, for example, some kind of a high-end analysis tools, high-end chromatographic analysis or any kind of such devices, there could be various pieces within that. They are like kind of composite devices with multiple parts, and some parts you may be replaceable units. So there are some set of fixed devices and there are some which are field replaceable. And a composite assembly entirely is what we talk as a individual device. In this kind of a composite device, the individual parts should also be identified and then should be validated. Say, for example, when you boot the system, you can make sure that all of these individual replaceable units, you validate that the individual replaceable units identities are correct, and then only the composite assembly accept it. And the security that comes is the entire composite should have the security, and you can also have identities for the individual submodules. And when you the parts replacement, when you replace a part, you should also make sure that the replaced part is once again a trustworthy part. So this is something which is a case which like if you are looking at say specifications like TPM, the TCG Trusted Computing Group's TPM, if you see, they have some explanation about composite devices, field replaceable units, and what are best practices. How can you give identities for these kind of composite units? Those are things which you can refer to for like even say I've the domain currently which I am working on for a server, for example, you can replace your network cards, you can replace your storage, and then your identity of the entire system has to be correct. And it is not that all the replaceable units are homogeneous. They could be homogeneous. Okay, we have very similar items together, or they need not necessarily be homogeneous. They can be heterogeneous units. So there should be identity for individuals of them. So it's not like you have that one communicating entity having identity talking to the further the next entity like your web server or your SCADA system or even your engineering station. That should not be the only case. Instead, it could be within the device itself you have various components which require identities of its own. That's where the composite assembly comes into picture. Now we talked about identities, but before we can trust about, and the best practice here is that the private key should never leave the secure element. Private key should remain inside. And then how do we know that as you boot, we talked about firmware. How do you know that as you boot? This is where the root of trust that is coming into. How do you know that you boot the correct firmware or not? That's where the secure boot and the root of trust comes into picture. So what typically happens is you have an immutable trust anchor, and the trust anchor is like as I was telling, there would be a signing key for your any kind of mutable firmware. You have signed it from your firmware developer, and that key, the signing key is corresponding public key. That's what we can, public key is public. There's no problem. You can put them into every single device. So you usually put it into a fuse array, that fuse array. It's because the keys, for example, RSA or ECC, they could be long. So you take a hash of the public key and then you put it there. So there would be one-time programmable fuses which are fused with these public key information or a representation of the public key in the form of a hash of it. And then as you boot, the very first changeable code, you see whether that very first changeable code is signed using the corresponding private key within the, which is put in the fuse array. So that means the very first mutable code is verified using an immutable code and an immutable key. And the ROM code, what we are talking, the first ROM code, that's also immutable. So you take your first immutable code should have the capability to verify the first mutable code. So that's what we say. So this means you need to have some capability within the hardware. It's not just a firmware. Within the hardware, the boot ROM should have the capability to verify the first changeable piece, and then you go further. So this is what happens. On the left side, you see the bootloader image, code signing. The signing key you should have, so the signing private key is used. So that is back in your firmware development firm. And then the corresponding public key or the hash of that, you put it into your fuse array. And then is the first image that you are coming signed or not? That is the first verification that happens. So once this first verification is happened, we have established a root of trust. So if you don't have this kind of a root of trust establishment, we cannot trust any further firmware that is running on that device. So then further in the next steps, what happens is, so first you see this red line, that is a boundary of transition from the immutable to mutable. So when you move from the first mutable code is verified and loaded using the fuse array with ROM code, and anything further, you can have keys which are known to the further mutable code, and any further application image is loaded after only the signature verification. This is where you have your the boot has your chain that is coming up. Every single image further is verified and then loaded. So the trust anchor, which we talked as the first one, the root of trust, the hardware root of trust, it help you to verify every single image. The ROM code, say I'm talking about bootloader, your U-boot or those kind of items, or the operating system could be the next one, Linux, and the applications coming it. I have just generalized it here. It could also be your virtual machine, your Docker, your container images, all of them. It could be any of them. Okay. Or after that, individual applications that are getting loaded, it could all of that be any of them. So further, you continue like this and then load every single image after the signature verification. Like if you are interested in knowing much more details into it, uh, like quite elaborate examples could be UEFI secure boot. That is one which you can look at. Like, but UEFI secure boot and all are not the kind of secure boot process that we use for very low end device. Very low end devices, still you need to have a root of trust, otherwise you cannot trust that. So using these root of trust, we verify that the every firmware that you load further is correct, and the identity which we talked about is used to establish that okay, this is the device which I am claiming to be, and I am able to provide you a facility to verify that the device that it claims to be is what it actually claims to be, based on the signature verification that happens from the signature from the factory. From the factory means from the device vendor. And what I was told about the supply chain, that it is told there are various mechanisms to establish that. So as it goes through various supply chain, you could provide further identities. That is one way. Or there could be things like voucher based mechanism. OPC way calls it tickets. So that kind of mechanisms that you can use, that okay, it has gone through various hands and now it has reached here. So you should be able to trace the physical device using your these kind of identities and signature across the entire supply chain that it has come to your hand, so that you can trust the device the way it is coming in. So this is what the concept which I'm coming to. This is what I wanted to explain. So as a summary, what we are telling is that security is not only in the firmware, it's also in the hardware, and the ability of the hardware to provide identities, to provide secure boot, to provide hardware root of trust, and the secure element to store its secrets. Because once you have certain secrets that you can store in the secure element, you can use that secret to encrypt your further volume. If you have volume of data, you can encrypt, and then ultimately you can come into a secure element which is physically protected within the device, and you can encrypt data and then store it somewhere else. So you can only tamper proof you can make it, like the confidentiality can be maintained. So you will have to maintain your confidentiality, integrity, tamper proofing, immutability, availability, all that you can maintain with your hardware root of trust and with your device identities. They are all centered around the ability of the hardware to provide identities, to have its keys, the facility to store securely the key, the private key information which is related, identity related, and then the mechanism to make sure that your firmware is secure by securing your boot flow path. Because once you have understood the boot flow path during the firmware update, you can use these keying information to make sure that the update firmware that is coming in is again signed and then verified. You can verify and then only update. So these are the contents which I wanted to talk about. So if you have any questions, comments, opinion, discussions, we could pick up that. John.
Yes, there are a couple of questions. Okay, the first one, who is accountable for subcomponents, device manufacturers or the subcomponent supplier for security compliance?
You are talking about this slide, the field replaceable units and a composite assembly.
Yes, we like in general.
Okay, if you are talking about subcomponent, see there is a, as I told, there is a trust domain transfer that happens. So assume that you are getting a replaceable unit. Say I'm talking about a storage card, for example. If I'm getting it from another vendor, up to the point where the assembly integrator, see, let me call it as the one which is creating the composite unit, up to the point that it is handed over to the composite unit manufacturer, the replaceable unit vendor has to own the security, and they should also be able to establish its own identity and say that, okay, it comes from, say, vendor A to vendor B is the the assembly manufacturer, and then the vendor A is the component manufacturer. The component manufacturer owns the responsibility to prove its identity, to prove that the firmware is secure, the device is not tampered, everything, up to the time it comes to the assembly, the one who is making that composite assembly. And then the responsibility of mounting into the composite assembly, verify that the individual replaceable unit is trustworthy, all that remains with the composite assembly person. So once you are selling the composite assembly, say for example the server or a kind of an analyzer which has multiple components, the one who sells the composite assembly owns the responsibility of the security of entire composite. But up to the time you have given it to the composite assembly manufacturer, the vendor, the sub vendor has to own it. And another reason why I say that the composite assembly manufacturer has to own it is the amount of verification that is required to be done as part of an acceptance procedure from the replaceable unit. You should accept it after verifying everything and then only even mount into your system. So I would call it as a shared responsibility. At the same time, within the field, if there is some kind of an issue that comes up later after selling it during the operation, if a known vulnerability comes up, say the OpenSSL, the initial which I was talking about, if something comes up, then it is up to the vendor A to make sure that they provide updates, they provide patches, they provide solutions to CVEs. That is their duty. But then keeping it updated, then mounting into the system, verifying it, and even flagging that, okay, this is not up to date. All those are the composite assemblies. It's a shared responsibility, but then there are still boundaries of whose responsibility till what point and whose responsibility further. Clear or anything further?
Yes. All right. So there is one more question. The life cycle that was shared,
Yes, yes.
was it in line with the IEC 62443 4-1 or 4-2?
IEEE, I mean, 62443 4.2 is where this all fit in. But then the component requirements are there, right? That is where it fits in. But then if you are looking at when I picked up this device lifecycle, I have referred to provisioning processes. That is where I came into. But it does fit into the 62443 framework. I just don't say 4.1 or 4.2 into the framework, because 62443 talk about the device vendors, then system integrators, owner operators, all those are talked there, right? In the 62443 context, like three talks about integration. So when you are talking about integrators, they come into supply chain, and owner operators, they come into provision and operation, even management. So this is in line with that, but I don't recollect from my mind that 62443 talks about such a life cycle. But if you look at the OPCUA device provisioning spec, they do talk about this, not in this same form, but OPCUA's device provisioning specification, they talk about this device lifecycle. 62443 from the top of the mind, I don't recollect them putting this kind of a diagram there or this kind of a life cycle, but OPCUA definitely they talk about
Right.
such kind of
Right.
life facility. But this is definitely in line with 62443. Considering the responsibilities which are defined in the 62443.
Right. So, especially with a lot of OEMs and manufacturers, product manufacturers trying to manufacture their own hardware or
Yes,
uh, so, uh, source it to third-party manufacturers.
yes.
So, in such a situation, what would be the best practices? Because I remember in general, people do a very high-level requirements for the supply chain management when it comes to security. Going in depth as a buyer may be a big challenge. So,
See,
what?
the thing is, you identity is something which you will have to. You should ask for hardware. Root of trust is specified in the 62443.
Okay.
62443 definitely specifies root of trust. And since I was talking about generic IoT solutions, the global platform talks about root of trust and the requirements for root of trust. 62443 has requirements for root of trust.
Okay. So what is the best practices or what is the documents that we should expect from the vendors or the suppliers? They may not be certified or they may not have any uh, certification related to security, but they might have their own internal procedures and best practices.
See, these are coming now with the standards. See, these are coming. I see when I'm talking about OPC UA, please take a note. I'm talking about OPC 10,000-21 UA Part 1 device onboarding.
10,021.
10,000-21.
Okay.
It's called device onboarding. They do define the way it goes through the identity certificate, the distributor, manufacturer, owner, operator. How do you put identities? How can you use URIs into that? And some concepts of tickets, which are used by FDO as a vouchers. This spec talks about it. How do you tell that? Some of them are already covered in 62443.
Okay. Okay. Understood.
Like root of trust is covered in 62443. Identity establishment is covered in root 62443. And it's also to do with the protocol. See, if you are talking about the protocol which are supported, say the industrial protocols for, like I just took a OPCUA as an example, that's all okay. Like
Understood.
if you are facilitating a FIDO device onboarding, FDO, not this industrial one, but a general purpose IoT, a device onboarding if you are talking about. They also talk about having an, say if you are compliant to a FIDO enabled device, if you say, then it should have all this. And device identity alone, you never accept unless you have a root of trust.
Right.
So it's like you can still demand compliance to the specs. Like it's not like they are all there from long time, but these kind of root of trust, hardware enabled security, the secure boot, identities, onboarding, those are all now in the spec, may not be in all the specs that we are talking. At least these samples which I talked about, they are in the spec. So you can use them as example and then ask for further.
Understood. So there is
Like
one more
ask basic
question.
questions. Ask basic question. Like first you can ask them, how do I know that, okay, this is coming from you as an OEM? How do I
Okay.
know that the firmware is not tampered?
Understood. Right. So there
Yeah.
is one more question with regards to firmware upgrades.
Yes.
So when we talk about the CVs or the vulnerabilities
Yes.
that are available, that
Yes.
are released,
Yes.
so
Publicly
manufacturer,
known CVs.
yes, publicly known CVs or whatever
Yes.
CVs that is researchers identify.
Yes.
So manufacturers have some kind of control who need to upgrade for installed base, such as any third party can also do it, or some lack of trust is expected in such cases?
Could you please repeat?
Okay, so is it possible to manage such situations
Hmm.
once the device is already installed?
See how you do it is, say when you do the firmware upgrade, uh, you don't allow somebody to upgrade the physical device verifies that the firmware is signed, it has a good signature coming from the OEM, then only you upgrade. Let me look
Okay,
at yeah, let me look at my diagram once. Okay, the boot sequence flow which I told, right?
right.
Here, okay, I did not have a firmware upgrade diagram per se. See, during the boot I have told that every single mutable firmware, mutable image as part of the boot process is verified that it is signed by a trusted entity, and then only you are loading it. In a similar manner, as you upgrade the firmware, see for example from the OEM, the device vendor only has to give you the firmware also, right? They usually publish it on their website or they have some distribution channel and you get it. So
Correct.
received firmware, you should be able to verify that the received firmware is coming from the same vendor. You should have
Okay,
some kind of root certificate which is with you, where you can verify either publicly trusted DigiCert kind of issued items or the vendor issued root certificate, which you can
okay,
take and make sure that the firmware which you are going to upgrade is already signed. If it is not
right.
signed, you refuse the upgrade process.
Understood.
So the
Understood.
upgrade fails. So upgrade will not be successful unless it is signed and verified.
Fine. All right. All right.
Okay, so that means it's not that the OEM has a control on the whatever the device vendors or owner operators are doing, but the OEM has put enough mechanisms so that a rogue image cannot be updated into the device.
Right. Understood.
But then the responsibility of actually doing the upgrade, because from a running system, nobody wants to shut down or put some kind of break time, downtime to do your upgrades. But then planning for that scheduling and doing the upgrade, that responsibility remains with the owner operator.
Understood.
There can be
Understood.
automated process, but still you have to allow that downtime to do that.
Correct.
Because on that, the OEM will not do, they will not get into control because you are operating your plant. You know that, okay, when can I afford to put it down?
Sure.
Because not all firmware upgrade process is seamless that, okay, it's still working on its primary functionality, especially on critical systems. Typically after the upgrade, it may ask for a reboot. And even that reboot time must be you wanted the control.
Correct.
Yes.
All right. So I think that's all the questions we have. Um, Anybody else would, we still have some time. So participants, if you have any questions, please raise your hand and we can unmute you so
Or
that
if
you
there
can.
is any topic which you like to go into details, like that's also fine.
Yes, so that's also fine. So make use of this opportunity. I think there is more focus into embedded security nowadays, especially with all the supply chain issues and so on. So
See, a while ago, like I say, maybe like some 4 or 5 years ago, or maybe some 5 or 6 years ago, when you were talking about IoT devices, there was always, what do I say? I think I should say some kind of an excuse or a hiding behind that, oh, IoT devices are very low end. I don't have compute capacity. I'm running on small microcontrollers, so I can't put all this security into them. But that days is over. Even if it is small embedded devices, even if it is small microcontrollers, you still need to have basic facilities for providing your device identity to guarantee that your firmware is good. And it is also possible that you don't need to run your very high-end RSA kind of items, right? There are the algorithms also are coming more popular, like elliptical curve cryptography, ECC, which are much more compute efficient. So it can be faster with less memory and less compute time. You can still achieve it. So it's that kind of the once upon a time excuse that these devices, I am at a low end, I don't have compute capacity for running cryptographic algorithm. That's all no more valid. If you want security, then do it.
all right,
Uh,
understood.
Good, yeah.
Yes.
Good evening, ma'am. Good evening, everyone. Ma'am, just few weeks ago, I read about the TX1 Stellar product for the OT security. So they are claiming that they have created a ICS root of trust in the endpoint security solution, that is Stellar one, and they have about thousand signatures or certificates from the OEMs. So, ma'am, I mean, this is just an information for me, and I just want to visualize. So, could you means explain a bit how could they have done this, making ICS root of trust of thousands of vendors, thousands of OEMs, and yes.
I am not very sure what exactly is the case that you are talking about. Uh, but then, are you telling that somebody is able to break the system? Is that what you are talking?
No, no, ma'am. I'm telling
No.
that Trend Micro's TX1 is
Hmm.
selling their product, which is known as TX1 Stellar, and they are
Okay.
claiming that
Hmm.
they have created an ICS root of trust in their endpoint security, where they have over 1,000 signatures from multiple OEMs. So it is just, I'm saying that I cannot visualize this thing. I mean, because I'm new to OT security. So first of all, like root of trust
See,
is.
ideally, I do not know what is the specific case that you are talking. But then if
Mhm.
somebody has to, like, I'm talking now the foundational concepts, okay. The
Okay,
case
ma'am.
which you are talking, I'm not aware, but then the foundational case is if somebody has to put a signature, you need to have the private key. And the private key is supposed to be kept private. That's why we call it private. And the private key, we should define who is the owner of the private key. The owner of the private key is the one who is actually signing. Like, say, if it is a manufacturer signature, it is that manufacturer. Is this could be some kind of business deal that the OEM has given, or they have some kind of business deal, and then they have manufactured, gathered thousands of signatures from multiple vendors. That could be one way. But the owner of the private key is the one and only one who has the authority to sign. And the private key should never be shared with anyone else. So the case that you
That
are
means
talking, I am not aware, but then could be a business deal, which I can imagine. But the very basic concept is private key should never be shared with anyone else other than the key owner. And if a physical device, of course, code signing, the one who develops the code and the one who releases the final binary signs it. That means the signing person has the responsibility to keep the keys secure.
that means, ma'am, without any collaboration from the particular OEMs, the same cannot be achieved.
At least I cannot imagine right now to achieve something other than collaboration, because you
Okay,
never
ma'am.
release the private key to anyone. That's a fundamental principle.
Okay, ma'am. Understood. Understood, ma'am. Thank you.
Yes.
But I need to read up to understand what that is specific case. But then,
Yeah. Good evening and good evening, ma'am. And thank you, Abhinav. I think a very good point raised. Actually, I'm not sure if I mean, I'm in the same line, just I'm extending the question. So TX1 example you given, and many other vendor nowadays is coming for OT security, and they are providing some sort of devices to put under the network and under the environment. So basically, what Abhinav example was, they are trying to say like their devices has been verified with certain sort of trust route
okay,
actually.
that could be that. Okay, if that's what you are talking, that means see, one aggregating person can take the root certificate. All of these are signed with ultimately the security is traceable to a root certificate. We are talking of a certificate chain. When I say a signature, I mean a certificate chain and a root certificate. So it could be, uh, so the certificate chain and the root certificate, if you are holding the root certificate, that can be your trust anchor. So if you have a root certificate, you can use that to trust whoever is deriving keys from that root certificates or the certificate chain. And if they are publicly trusted, typically these devices will not be publicly trusted root certificates. So they will be individual vendors. So see, the case is, say, for example, let us look at a typical web server. If you are looking at a typical web server like your HTTPS www.google.com and the associated HTTPS certificate, when we are looking at such kind of an entity, they are typically publicly trusted root certificate. They are distributed by your Windows or the Linux distribution. But when you talk about individual devices, they will be a vendor specific one, and because they don't actually follow the CA browser forum, CAB forum rules, and they cannot do that because these are all long lived keys. Uh, you don't rotate the keys. There are various constraints. So typically these will be your
So ma'am,
OEM managed or vendor managed. So
okay, thank
so
you. Just
having the root certificate, you can establish the trust.
okay, thank you, ma'am. Just in short, the question was: suppose if I'm deploying that particular component or device in my network,
Yes,
so because they are giving lot of, because there is a chain, there's some component
yes,
by other, and they are giving lot of, I mean, with
yes,
hundreds of thousands of. So how, as a single point of, suppose I am the user, how
yes,
as a user I can 100% make sure that what he is giving, irrespective of hundreds and
yes,
thousands, that yes, it has gone through the process and it is there
yes,
any way that in
yes,
a
yes.
single
That is
point
the
we
root
can
certificate.
verify?
That is the root certificate. When you
Okay.
are looking at a certificate chain, when you are seeing a certificate chain, digital certificate chain, having a root certificate, if you have one root certificate, any certificate that is derived from any of the child trees, you can trust any of them that is derived out of it.
Okay,
So
thank you.
just by having one root certificate, you can trust a whole bundle of items.
Thanks, got it. Yeah, thank you.
The certificate chain is there, right? The leaf node. You can trust the leaf node or any other node in the intermediate if you hold the root certificate. And during the TLS exchange, for example, TLS, I'm giving an example. The entire certificate chain is handed over to you. How do you trust that? Because you have a prior known root certificate with you already. That's what we call as a trust anchor. So if you have an anchor, you can trust any of that coming from the same place. Yeah, I think I got what your the context. Okay, so if you have some bundle of root certificate, which are trust anchors, you can trust a large number of vendor contents from that. What else?
Any further questions from the participants? All right then. So if no further questions, then we can conclude.
Thank you. Thank you.
The feedback will be shared here. Do share the feedback form, and because your feedback will be very helpful for us to do more such sessions and improve it. And you can also please join OT security professionals on LinkedIn and even the WhatsApp, and share with your friends and colleagues and your network. Thank you again, Mini, for joining us today and sharing about the device level security concerns and how to go about it. It was a very informative and insightful session. Thank you again. Good evening, and thanks everyone for joining today. Yeah.
Thank you. Thanks the audience for your attention during the time, and thanks John and all of you for making the arrangements.
Thank you. Thank you.